I will. Yep, definitely. Okay, it's being recorded, I believe. Yes, it is. Okay, let me officially start. Okay, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Michael Mahoney, who is a professor at the University of California at Berkeley in the Department of Statistics and at the International Computer Science Institute, ICSI. He's also an Amazon scholar as well as a faculty scientist at the Lawrence Berkeley National Laboratory. He works on algorithmic and statistical aspects of modern large-scale data analysis. Much of his recent research has focused on large-scale machine learning, including randomized matrix algorithms and randomized numerical linear algebra, geometric network analysis tools for structural extraction in large informatics graphs, scalable implicit regularization methods, computational methods for neural network analysis, physics-informed machine learning, and application in genetics and astronomy, medical imaging, social network analysis, and internet data analysis. As you can hear, pretty much everything he touched on. He received his PhD from Yale University with a dissertation in computational statistical mechanics, and he has worked and taught at Yale University in the mathematics department, at Yahoo Research, and at Stanford University in the mathematics department. Among other things, he's on the National Advisory Committee of the Statistical and Applied Mathematical Sciences Institute. He was on the National Research Council's Committee on the Analysis of Massive Data. He co-organized the Simons Institute's fall 2013 and 2018 programs on the foundations of the data science. And there are many awards he got, and more information is available at his webpage. Okay, today Michael will talk about toward combining principled scientific models and principled machine learning methods, which is very interesting topic. So please enjoy and expect a wonderful talk. And now, without further ado, let me pass the baton to Michael by asking one random question as usual. Today's random question is, what is your favorite things to do other than research?
What's the favorite thing to do other than research? That's a good question. And I'll tell you something that I haven't been able to do in a number of years, but so I wouldn't say I did it a lot, but I did it a number of times and I enjoy it and I hope at some point to get back to it. I like to go scuba diving.
Oh, wow.
And occasionally
Wonderful.
people say, "Oh, I do that. I do snorkeling." And in a sort of teasing way, I say, "The only reason you like snorkeling is because you've never done scuba diving." I mean, they seem to me qualitatively different, and I'm not sure why. It just seems very sort of. I like the beach, but not. I mean, the beach is okay, but then you get sand in your shoes and it's a little messy. But going into a different world, where you're underwater, and so on, it seems very otherworldly. So I'll do a thumbs up for scuba diving. How about that?
That's great. Sounds dangerous though.
So scuba diving, I mean, like a lot of things, driving a car is dangerous, right? If you know nothing, it can be. But I took a class, actually, a fun fact before I begin. So it was mentioned that my PhD was in computational statistical mechanics. After that, I moved to theoretical computer science and large-scale statistical data analysis and worked on that for a number of years. And now in the last couple of years, gone back and looked at sort of scientific machine learning problems from the perspective of ML, but knowing a lot about physics.
Right.
So my dissertation was in liquid state statistical mechanics. And so there's a lot of models for water. You want this for protein hydration, and you know, so it wasn't icing models in your phase transitions. It was liquid state. And so the state of the art, then the centerpiece of my dissertation was getting a model for liquid water that was as good as the best existing models. And in addition, got on the nose the temperature of maximum density. And that was important, you know, for a range of reasons. It wasn't clear you could get that within the class of parameterized sort of simple interaction site models. So I'm wrapping up my dissertation, and it's a bunch of things related to this, but this was sort of the centerpiece. And it was at that time that I thought, why don't I try out scuba diving? So this wasn't a total non sequitur. It gets back to the scuba diving. So the point is, I was the world's expert in the density properties of water.
Right.
Literally. And so I think it was the last or second to last semester before the dissertation was wrapping up. And scuba diving can be dangerous, but if you get certified, and I had a very good class actually, where you walk through the physics of stuff. So if you're down at 50 or 100 feet, you can constantly breathe out if you have a problem and shoot straight up to the surface. It's a problem if you're in a cave or in a boat, you know, under a shipwreck or something. So you got to be a little careful. But you can just constantly breathe out and avoid bends and, you know, things like this. And it's just PV equals nRT. It's basic physics and basic chemistry. So I took a class, you need in water, I need a written exam, and I got one question wrong on the exam.
What is that?
And that had to do with the density of water.
Which you are an expert on it, right?
I mean, the answer is 0.997 in the units I always used. The units on the test are units I didn't know, you know, it's force pounds versus inverse light years or something. I mean, it was units I didn't recognize. And so I pulled the only number, I marked a check next to the only number I recognized, which I just recognized from reading the book was the density of air. So it was a factor of 1,000 off. So I just recognized the numeric value, but didn't recognize the units. So that was sort of a lesson for me in, so literally the world's expert, I got the density wrong. So this was a lesson in how to design tests that really extract whether someone's learned something. And so I teach classes now, and that's sort of something I keep in the back of my mind.
All right, great. All right, thank you, Michael. Stage is yours.
So that's a long answer to the fun fact. I hope you don't have a second fun fact question. We'll never get
no. It's all let's go to the technical now.
But that was sort of a preamble, which wasn't a total non sequitur in the sense that you know, I did computational statistical mechanics, and so I was a user of linear algebra and a user of a range of sort of techniques. And in the last however many years, sort of developed them in the context of machine learning. And a lot of scientists, I mean, I worked at industry, but also like scientific problems. And it's a source of endless frustration for me. So hopefully people in this room or audience are listening and will meet me either halfway or quarter way. So oftentimes what people say is, oh, I want to use machine learning for such and such. And in my answer, being sympathetic to the scientific problem such and such, but also realizing this is an interdisciplinary space and different areas have very different standards, I want to say, yeah, but I want to use such and such for machine learning. So you have a scientific problem. What can you do to help me, not vice versa? And I think framing the question that way is sometimes useful for people to think about, because otherwise I'm a machine learning person and I'm just a tool that gets buried in a methods section at the back of your paper. And of course, the flip side is if I publish in a machine learning venue, I publish a toy scientific data set or a toy non-scientific data set, and the ML people don't care about the details of the data set, they want the method. And so what I want to talk about today is sort of trying to get beyond that and trying to combine what I'll call principled scientific models with principled machine learning models. And so we did a lot of work on randomized linear algebra and other things over the years that really sort of are very interdisciplinary. And oftentimes the best methods there, the reason the two areas are interested in them are different and sometimes inconsistent. You know, area A likes the method because of such and such, area B likes it for basically an incompatible reason. Worst case versus statistical properties, interesting properties qua machine learning or generalization versus usefulness in the scientific domain, they can be very different. And so what I want to do today is to try and sort of lay out, you know, it's a toward combining, so it's not the final word, but a progress report on some of the recent experiences we've had with trying to get, you know, methods that are really interesting qua machine learning, but mapping in very non-trivial ways to sort of scientific methodology. All right. And so something that's very common in scientific problems is modeling space and time. And so we're going to be dealing with this. And so we want to be modeling spatial and temporal behavior. And that's something that's not obviously first class in machine learning, right? In machine learning, you define features. The data may come from a spatial domain, but maybe not. If you're working on computer vision, there might be some structure to the image, but you might be working on internet ads or something where there's not an obvious spatial component. And so think about what's peculiar about space and time, especially if you want to be applying machine learning methods. So how can we integrate domain insight with data-driven methods? This is going to be the basic question. And when we started the tripods and the foundations of data analysis institute at Berkeley, we had a couple of foundational questions, just scalable algorithms and statistical inference. But one of the foundational questions was, how do you combine in a principled way domain-driven models with data-driven models? And so that's sort of the question we want to address. One thing that's gotten of interest in recent years is neural networks. And so I'll be talking about two examples of that. But I think the basic question's more general than that. And we've had results over the years where we've thought about that. So that's informed our sort of approaches here. All right. So I want to talk about sort of two main topics. And then I want to just mention a couple other related developments at the end, just to sort of put it on your radar. And have me back in a couple of years, and I'll tell you about how those results play out. I mean, we have I think I have a pretty good idea of how those will play out, but they're sort of recent developments that are work in progress having to do with the temporal sequential properties. I want to talk about two other things we've been thinking about for a number of years. The first has to do with physics-informed neural networks. So physics-informed neural networks are a class of models that a particular group of people have developed. And roughly the idea is I want to minimize a loss, like in machine learning, and I tack on domain insight as a regularizer. It's a special case of what's going on inside of scientific machine learning. And we want to study a particularly simple version of that to understand what's going on from the machine learning perspective, and in particular from the optimization, stochastic optimization perspective. And what I think we'll see is that we're going to be able to identify some failure modes with tying those two things together in sort of a vanilla way. And I think if you tie them together in a somewhat non-vanilla way, you still have the same failure modes, and they have to do with sort of what it means to have a constraint, a physical constraint versus not physical constraint. And is the constraint a hard constraint or soft constraint? And these are sort of details of the optimization that machine learning methodology handles in one way, and in some cases physically you need to handle in a very different way. And so the idea in the back of your mind is usually machine learning constraints are just suggestions, and so you just need to satisfy them very approximately, if at all. In a lot of scientific problems, constraints are important. If you want to constrain your energy and you want to iterate your simulation, if you don't conserve energy, your simulation blows up. And so it needs to be handled in a much stronger way and respected. And so there's some interesting issues about the details of the constraint that I think that work sort of highlights. The next thing I want to talk about, again, is something that matters scientifically, but also matters qua machine learning. And this has to do with the idea of continuity. In most cases in machine learning, you do training and testing on a given set of data, and it's basically discrete. I mean, you can put a T there, and call it continuous, but basically the methodology, the design decisions that you make are discrete. And if you want to learn something like a continuous model, how do you do it? I mean, oftentimes you'll specify a set of basis functions, learn parameters for those basis functions. So qua machine learning, you're really learning something discrete, those parameters. You fix the basis functions. You might try and adjust the basis functions, but where does continuity really enter? And so we'll get to that. But in the back of your mind, before we get to that, ask yourself, a version of this question already appears in numerical analysis, right? In numerical analysis, in scientific computing, you typically think, geez, I have a continuous PDE, but I can't write down a continuous thing on a computer, so I discretize it. And so what does it mean for a discrete representation of a number to be approximately continuous? So what does it mean for a discrete algorithm, a numerical integrator, to meaningfully approximate a continuous function? And so how would you quantify that? I mean, and so we'll get to an example of how to do it. So numerical analysis is a range of ways to quantify that, and we'll use some similar ideas there. So details of the optimization, details of what it means for discrete things to approximate continuous things, clearly both important on the scientific side, but also cutting across the way ML methodology is usually developed. And the other related developments that will basically be having to do with time series, temporal or sequential modeling. Time really doesn't appear in the structure of a lot of modern machine learning. It appears in econometrics and sort of older school sort of statistical techniques. But a lot of modern machine learning, think kernels, think boosting, think neural networks. I mean, it's classification, it's regression, it's ranking. I mean, so time doesn't really appear as a first-class citizen. You sort of graft it on separately, if at all. And so can you get beyond that? And so those will be sort of the things I'll mention at the end. All right. And this is a slightly different form. Usually I have Zoom and some things on the side. So either interrupt if you have a question, or if there's a channel with that you can post comments. And I can't see that, but post the comments and either someone can interrupt during or after with questions. I'm happy to do it either way. All right, so let's talk about understanding what can go right or wrong when you're trying to couple machine learning methodologies and scientific methodologies. And let's use these physics-informed neural networks just as an example. So physics-informed neural networks are a class of models Karniadakis and others have developed that it's a nice, very nice sort of hello world way to do a range of things. And they've done a lot of work there. And I sort of like them because, it's not the final word. And for some things you want to do other stuff, but it was a nice sort of, let's call it hydrogen atom for us to sort of look at how ML methods and physical methods sort of might couple together. So the usual approach in machine learning, think ridge regression, if you want to do that, is sort of given on the right here. You have an optimization. I want to minimize the least squares or some loss, and maybe I have a constraint. It's an L1 or it's an L2. It's a ridge regression or lasso constraint. So I optimize F plus lambda G. I make it a soft constraint. It could be a hard constraint. Minimize F such that G is equal to some value or less than equal to some value. But the way it works in machine learning is you take that hard constraint, you relate it with a soft constraint with this Lagrange dual mechanism, and so you basically minimize F plus lambda G. So the physics-informed, the PINN approach does something different. You have a bunch of data points, and I want to minimize the loss on those data points. But then rather than using an L1 or an L2 ball, the constraint is basically a linear differential operator. I mean, on the left I have a particular example, Berger's equations for fluid flow, but you have a linear operator, and so it's a differential operator. And so let's just use that as the physical insight, the domain insight, and tack that operator on as your constraint G, although here I'm using the letters L plus lambda F. So minimize a bunch of data points subject to a constraint that's given by the physics. Now, a question that comes from this form, I mean, so you're not going to satisfy, neither of those are going to be zero exactly. So you're already in the Lagrange dual and optimizing this approximately. Now, the usual interpretation of this is, well, there's a trade-off. If lambda's 1 or 0.1 or 10, these two terms, one matters more or less. The fact that there's a lambda here, I mean, people might say, well, I could set it to be 0 or non-zero. As long as I stay away from 0 infinity, I could put lambda before this, or I could put lambda before this. And I think in a lot of people's mind, the data is primary, minimizing the loss, and tack on the second term as sort of a prior, biasing yourself towards, small norm balls, or in this case, physics. In a lot of physical applications, I think it's sort of reversed. And this constraint, the physical thing, the structure of the PDE matters more. And so you should think of the lambda as being over here. Now, of course, it doesn't matter if you think of lambda as permitting it to be 0 or infinite. But when the problem's set up, and then if you call black box code, you can get very different results in those two cases. So what the PINN approach does is adopt sort of an ML methodology. Now, the first thing to know for machine learning is that there's a range of typically stochastic optimizers, first-order stochastic optimizers, stochastic gradient descent. Now, vanilla stochastic gradient descent doesn't do so well. And so you get a range of variants of it. There's SGD with momentum, there's atom, there's attigrad, there's a whole zoo of methods, and they all have hyperparameters. And it turns out that in the best variant of SGD for computer vision is different than the best variant of SGD for natural language processing, is different than the best variant of SGD for recommendation systems. And it's also different than what what people would use in PINNs. I mean, in PINNs, oftentimes people would use LBFGS or something like that. That's not what's used in those other areas. And so even the stochastic optimizer itself becomes a hyperparameter to fiddle with. And so the question we wanted to ask is sort of how does this behave if you call any of a range of optimizers with an ML methodology? And so the long story short is we see that this method will work pretty well for nice values of these various physical parameters, and they'll break pretty quickly for not nice. Now you could criticize us and say, well, you should use Atom Prime or Atom coupled with LBFGS coupled with something else. I think the qualitative points we'll be talking about loss landscapes and the details of the optimization would hold true. I mean, future work, I mean, prove that right or wrong, but I think that when the dust settles, that'll be right. And the lesson here is you need to go beyond that vanilla coupling to extract insight from scientific problems. So this is the TLDR, and I'll walk you through a range of examples on some slides. So we investigated PINNs, and we looked at a range of common problems: convection, reaction diffusion, and from the ML perspective, they're all the same. They're just some PDE that we want to deal with, right? Of course, scientifically, they're very different. So the question is, we want to combine in a principled way the two areas. And so we want to get a little bit beyond just the vanilla cut and paste, but we also want to do it in a way that, from the ML side, views them as sort of physical things as opposed to the universe of other things that it could be, which is, natural language or whatever. So a bunch of work here on PINNs, a lot of nice work that sort of informed what we're doing. We're going to investigate these three. I'll walk through one in a little bit more detail and the other two in a little bit less detail. So let's say we want to learn convection with PINNs. We have the differential equation up here. Beta is the convection parameter. In this particular case, you have a nice clean analytical solution that we're going to be able to compare against. We have initial conditions and periodic boundary conditions. So the loss that I had a few slides back takes this form. We have a loss, which is, a sum of squares, plus lambda, which is a Lagrange parameter, plus call it L sub b, which is an L2 for the boundary conditions and initial conditions. So we're not satisfying this in a hard way. We're satisfying in a soft way. And now let's call this with some optimizer. And we've interacted with the PINN people. They say, well, do this particular protocol with Atom and LBFGS. We didn't know it at the time. Our code's publicly available, so do a git pull if you want to compare against this. We compared with what we could in terms of what was available. And what we saw is roughly the following. The quantitative values will change depending, I think, on the specific optimizer you have. The qualitative points, I think, will be robust to this. At low speeds, at low values of the beta parameter, the PINN learns a good model. So on the left here, we have the error between the computed solution and the correct solution for this convection problem. And as a function of beta, you see that error, it's not 0, it's actually 10 to the minus 3 or something. So it's not great. And a lot of these methods seem to peter out at 10 to the minus 3 or 10 to the minus 4 for reasons I think that are probably partially understood. And as beta gets larger, it gets worse. And then at some point, it sort of chokes and there's a sharp transition. And the exact solution on the right is shown for beta equals 30, where you're in this regime after it's choked, and the predicted PINN solution. So you get something very, at early times, it satisfies the boundary conditions, right? You see here the bottom matches up to the top, but beyond that, you have basically a problem propagating the information. All right. So beta equals 10. Before you have that problem, you get perfect, basically perfect resolution, reconstruction. This looks sort of bad, but look at the scale of the y-axis on this difference. It's a couple orders of magnitude less than the second and third row. So basically, the eyeball test says that the predicted and exact solutions are the same. Beta equals 50, beta equals 70. It gets much worse very quickly. All right, learning reaction. You see the same thing. It's a different differential operator. Periodic boundary conditions, initial conditions, loss function of the same form. For small values of rho, it's not beta. It's a different physical parameter. If you're less than 10 to the 0, we should probably have the larger range of rho here. But if you're less than 10 to the 0, less than 1, the quality is a little bit worse than you saw before, but down at just above 10 to the minus 2, and then it chokes and has a problem once you get up above 10 or something. Training a PINN is going to be sensitive to the initial value. The exact solutions on the left, the predicted solutions on the right. Here's for rho equals 5 or 10, which is in that regime where you have problems. If you're depending on the resolution of the screen and your eyeballs, you get something here. So it's not all purple, but it quickly degrades. Reaction diffusion, same sort of situation. Here you have a new and a row parameter, but the same sort of setup, initial conditions, periodic conditions, loss function of the same sort of form. And similarly, exact solution, predicted PINN solution. You just have a, in this case, you actually do propagate the middle region through in time. We could be better or worse if we vary those parameters, but it fails to learn sort of the full physics in some sense. Now, this is not an expressivity problem. The network can learn this. This is an issue about the optimizer. And so the point is, you can say, well, you should use this optimizer or that optimizer. I think in ML, there's not good theory to guide why different optimizers perform. People typically will use stochastic first order methods. There's lots and lots of papers having theory that having to do with how these methods converge in nice convex problems, with very, very little that really provides qualitative or quantitative insight into how different versions of stochastic optimization methods would perform on realistic CV, NLP recommendation systems, scientific ML, I mean, sort of problems. And so I think this is a nice sort of open class of problems on the ML side. So challenges with PINNs, we started a bunch of basic things. We saw that coupling these things together in ways that would be very natural for an ML problem had very sort of immediate choke points. And so there's failure modes. And the failure modes is, I mean, I don't want to say we couldn't have done better on the PINN problem itself. We can, and others have in subsequent work to these papers. What I want to say is that when viewed from the perspective of the ML methodology, there's these natural failure modes that the two sort of approaches don't impedance match well. So I'm gonna provide some evidence having to do with that. This has to do with the form of the differential operator. And then I want to provide sort of two ways to, quote, solve this problem that I think if you're in machine learning, you'll say, yeah, that makes sense because that's a learning paradigm I can appeal to. If you're on the science side, you'll say, yeah, that's trivial. That's what I would do anyway, which again gets to the comment I made before that the standards of these areas are sort of very different. So if you look at the loss landscape via, say, the Hessian, the second eigenvalues, if you look at the loss landscape, what we see is something that's sort of rather unusual from an ML perspective. From an ML perspective, if you add more regularization, the loss landscape typically gets nicer and flatter. And what we see here is that that's not the case. If we add more regularization, and we see it very strongly as a function of this beta parameter, let's say the physical parameter that we either learn or don't learn as we change that, what we see is that the landscape becomes much choppier. And the scale of the y-axis, the scale of the non-niceness gets much worse. And so we're adding this with a range of other things that I'm not going to have a chance to get into, I think is arising because we're calling a black box ML method to solve this. And the usual thought is that these regularizers are nice convex balls. And that's not what's going on here. What's going on here is that these are differential operators that will have a non-trivial null space and a range of other things like that. And so solving the problem exactly, quote exactly, or with a reasonably high quality method like LBFGS versus solving the problem approximately with a Lagrange dual and a stochastic optimization is just very different. They're just very different. And so I think what the state of the art in PINNs now would do is run a stochastic first order method like Atom. It's sort of like a temperature annealing and then run LBFGS. And so they're doing sort of an explore phase and an exploit phase, which is consistent with what we're talking about here. But here, as you add more regularization, in a lot of times the loss landscapes gets worse. And I think that's because probably of the non-trivial null space. So open question, how to come up with better stochastic optimization algorithms for constrained optimization, dealing with non-trivial null spaces. That's sort of a nice sort of question raised by this work. And so you see that similarly that was as a function of beta, this is as a function of lambda. Was there a question? All right. Was there a question?
I don't know.
Okay.
You can go on.
So now, what do you do with this? And in machine learning, sometimes people complain that machine learners sort of do an old thing and just give it a new name, and then some truth to that and some not truth to that. So I want to leave that discussion aside for a second. But there's two approaches that would be natural in machine learning. And one's going to be called curriculum regularization, and one's going to be called sequence-to-sequence learning. Curriculum regularization roughly says start training the neural network with a simple ODE or PDE and then make it problem harder. So choose a nice value of the beta parameter and then increase it. Show the problem nice data and then gradually make the data worse. Sequence-to-sequence learning is instead of predicting the entire state space, start at the left and march to the right. I think both of these things are sort of the obvious thing from a scientific perspective. And so you might say, oh, that's not so interesting. The interesting thing here is that an approach in machine learning to get good inference, to get good generalization, is to do empirical risk minimization. You know, minimize error on the data points, and if your model class isn't too bad, et cetera, you get good inference. That's sort of bread and butter of machine learning theory. That's not what neural networks are doing, because the backprop step damages that, but you know, you can do that. So then if you're doing neural networks, because of the backprop step, can you get good generalization? So there's a lot of work on that. These are sort of, call them learning paradigms. They're ways to frame a problem such that if you interrogate the data in a certain way, you might get certain inferential guarantees. Now you might say, oh, this is the obvious thing to do from a scientific perspective, but getting that right qua machine learning and qua statistical learning theory is rather non-trivial. And so informally, you can think of curriculum regularization as a little like simulated annealing, except you're not changing a temperature parameter, you're changing the physical parameter to make the data easy to hard. But this is a hard thing for machine learning to deal with, because now you're having a change in the distribution of the data, and a lot of the theory doesn't deal with that so well. So these two approaches are nice, open questions qua machine learning here. And I think if scientific machine learners engage this more aggressively rather than less aggressively, it would inform how machine learners frame their questions to be more useful for scientific ML problems. So if you do both of these, the method does better. So curriculum regularization, here's the beta parameter. You start with the easy values and anneal up to the harder values. You go from the left to the right. So if you do this, you do better. So the networks have the capacity to learn this. And if you anneal the quality of the data, analogously to simulated annealing, but now you're basically annealing the quality of the data, you can get good results in the convection problem. Similarly for the other problems, here's some numbers to justify that. Similarly, in the reaction case, you can go from the plot we had before, where it's basically all purple. Here, the quality is a little less good, and there's some non-trivial structure there we're trying to understand. But basically, you can learn this on the bottom right, which is roughly what we had. Some of the curvature properties of this are a little bit different, but you get the sort of coarse properties right. The loss landscape, one thing that was interesting here that we didn't expect is the scale of the y-axis stayed similar, meaning that's a function of beta. But the choppiness got much nicer, meaning that as we annealed this, the choppiness of the landscape got better, even if the scale of the y-axis got better. And so this has, I think, interesting implications for learning from non-trivially structured to non-convex regularizers, namely, for example, differential operators with these non-trivial null spaces. If you do the sequence-to-sequence learning, roughly you march from left to right. Rather than learning the whole state space, you march from left to right, and you go from the middle to the right, which is a much better approximation of the left than the middle, clearly. Here's some numbers to justify that these are in the papers. This is actually the first PINN paper. It's going to appear in the NeurIPS, which is the top ML venue next month. This is actually the first PINN paper on machine learning in a machine learning venue. All right, so I think PINNs is a nice example of things in general, but it's a very simple setup to begin to ask how we can bridge the gap between scientific models and machine learning models. And I think we just identified a number of failure points that were interesting on the ML side. You might say, oh, this is trivial scientifically because I would have done this otherwise, but vice versa. There's things that the ML people think are trivial that scientists spend a lot of time on. So I think coming up with principled ways to bridge that gap, this is an example of how to do that. And I think we opened up a bunch of interesting questions that we're following up with, both on the ML side and on the scientific side. All right, so I'm not going to go into those follow-ups because I want to give you another example of this and any other failure modes. And here's one that I think is particularly interesting and may be relevant for a lot of people who work on PDEs of various forms in particular. Let's say we want to learn, people talk about learning physics, learning F equals MA and learning. I mean, what does that even mean? What does it mean to learn a continuous model from discrete data? So the intuition might be, geez, I have a lot of points and I just discretize very finely, and you see obviously that curve is sort of smooth, and so it's sort of approximately continuous. But probably a lot of you know there's a lot of sort of mathematical subtleties there, and people in scientific computing and numerical analysis spend a lot of time worrying about it. So what does it mean for a discrete model to approximate a continuous model? So let's go into that. So continuous in-depth neural networks. So this is going to be a structured class of models that's gotten a lot of attention in ML, where you can vary a depth parameter. And in the setup we have, we're going to be learning dynamical systems, and you should think of this as a 1/time parameter, right? So ResNets are a class of models that have gotten a lot of attention in machine learning for certain problems. And roughly what they do is the following. You have a state at time, call it time t or depth t, that's x of t, and I want to go to x of t plus 1. And this edge means that in the model I have a link between these two states. And so t plus 1 might be the same as t, but I also learn some difference. You know, the future state is the current state plus some difference, and call that a residual unit. And there may be stuff going on here that we don't do or don't understand, but it's something. So recent work has pointed out that the structure of this, if you were to write this picture as an equation, this is x of t plus 1 is equal to x of t plus a residual. And if you slip a delta t in here, and don't make it 1, but make it delta t, that's going to be important if we get to, you know, it looks a little like a different discretization of a differential equation. So can we slip that delta t in here? Is this syntactic form enough? And the spoiler alerts that it's not. No, it's not going to be like. So what we want to do is to come up with a meaningful way to think about these sort of continuous problems. So what does it even mean to learn that when we say ResNets learn forward Euler representation of a dynamical system? That was an Euler discretization. So one way to answer it is, you know, can sort of have a situation where a dynamical system is meaningful. So let's look at a few sort of hello world versions of that and see if it is meaningful. What you should note is that we're doing something very different than what's typically done in scientific computing and numerical analysis, right? There, you start with something continuous. I want to integrate sine of x from 0 to pi. I discretize it into a bunch of pieces, and then I do the trapezoid rule or whatever, and I add up the pieces, and I get, you know, whatever the integral of sine of x from 0 to pi is. And if I cut my trapezoid steps a little bit smaller, you know, I might get a better result. Maybe I shouldn't use trapezoid. I should use a higher order integrator because I can get the same quality with a smaller number of function evaluations. That's a very typical thing. And so what you're doing is you're quantifying the extent to which this discrete thing is close to the continuous thing by a sequence of models, and you say they get sort of better as delta t gets smaller. We're really going in the other direction. We have a discrete thing, and we want to say, are you learning the continuous thing? Now, there may or may not be a continuous thing here, right? I mean, I could be doing a PDE, but if I'm applying ResNet, I could be classifying images into cats and dogs, right? So this continuous thing might be a physical differential equation we want to learn. It might just be that we want to say we're near a continuous model because that might provide sort of capacity control in the machine learning sense of the word and be a good model, even if there's not really a continuous model under the hood. So really going in the other direction, I want to keep that sort of in mind. So let's say we have a dynamical system. We're gonna study that, and we're going to be learning basically a residual that says the future is now plus an update. And so we're going to study a training such that the x of t plus 1 or x of t plus delta t is some function that is the original delta t plus some difference g, let's call it. And think of this as a numerical method on G. And so numerical integrators will approximate the integral with a discrete series of applications of this. We have some scheme, and so we're going to try and do something analogous. So the point here is going to be that syntactic similarity, just this sort of syntactic similarity of the Euler discretization really is not enough to say that this particular discrete model is a meaningful approximation of the continuous thing. In numerical analysis, and we're going to apply those ideas to come up with basically a convergence test for a sequence of machine learning models to say that these models are meaningfully learning a continuous model. So for a given integrator, let's say that we cut delta t in half or quarter or eighth, which might mean double the number of layers or increase the number of layers. So it's basically a notion of time step refinement. The error should go to 0. If you're going to learn something meaningfully continuous, the error should go to 0 as you get more continuous, as the discrete thing becomes more closer approximation to a continuous thing, in the sense of this time step refinement. In addition, integrator A, model A, may be better than model B if the rate of convergence is faster. And so, the same dx dt with different integrators, I should be able to substitute different integrators, and they should approach the same solution at their respective rates, for example. So we can verify these things using a convergence test. And so the idea of these convergence tests is critical for a lot of numerical integration schemes in PDEs and elsewhere. And so we're applying it in machine learning in a sense. So do ResNet units satisfy these properties? If yes, then we should be able to take a sequence of models and alter them in very particular ways and see them get better and worse in very particular ways. If no, then the model should just behave in some way that doesn't respect the continuity properties, which is very different. All right, so here's what we're going to do. Run a set of experiments, make a data set with one delta t. Delta t is 1, or it's whatever it is. We're going to train 3 models using G, and then we're going to freeze G and perform that convergence test. And the hypothesis is that A, B, and C, the things we had on the previous page, should hold. So they either will hold or they won't hold. So the 3 models are going to be forward Euler, the thing we had before, midpoint, which is sort of Euler plus plus. You do a 2-step version of it. If you're familiar with midpoint, you know what it is. And if not, it's a slightly more complicated numerical integration scheme, which we could instantiate in a model where the residual block has some internal structure that is a couple residual blocks with certain weights. And we can also go to RK4, which is yet a better numerical integrator, but in certain senses, where you have a slightly more complicated residual block. So, where you have a bunch of residual blocks that talk to each other in a certain way. And I'll have a picture that we'll put up like this. And so we'll work in one case for ground truth where we have an analytical solution. In another case, we'll look at some error, and I'll show you something. But for the simple first case, let's look at where we have a ground truth solution. So let's train the models. They all perform well. And so there's a ground truth, which is in blue. There's a numerical Euler in orange, which does well, but then it diverges, meaning just numerical analysis of Euler. And then there's the learned model with the ML protocol I just gave you with Euler and RK4 in green and red, and they're right on top of the blue. You can't see a difference. What you see here on the right is that, well, this is 2 different, this is a space and a position, but you see in both cases the Euler gets worse, but then the ML models do sort of very well there in both cases. All right. So now let's look at what if we cut delta t in half? Now, if we cut delta t in half, what you see is the orange gets better. The orange is the numerical version of Euler. So the numerical analysis method gets better, but what you see is the green. Remember, the green here is the ODE Euler, the learned neural network. The ODE gets worse. The ODE model, the ODE-net model gets worse. The RK4 doesn't. If we go out longer, it may, but for right here. So this is already a warning sign that the numerical method's performing as it should, the ML method's not. Let's go beyond sort of 1-point estimate. So look at the plot on the left. So what you see here is in red, when I train at delta t equals 0, or the delta t equals is 10 to the 0, 1, and then I apply the model at a half, a quarter, an eighth, a 16th, 2, 4, 6, 8. What you see is that the quality, this is log scale on both axes, the quality of the model is pretty good at 1. So it's a good discrete model. The error is pretty small. But if you apply it at different delta t's, it just totally chokes. There's this egregious sort of failure mode where it doesn't pass the convergence tests at all. So it really, really is not a meaningful discrete approximation to anything continuous. It's a good discrete model, but not good continuous model. If you apply it to midpoint or RK4, the model gets better sort of gradually as you get more time steps going from the left to the right, a smaller delta t, deeper depth. There's 2 very different slopes, and before it sort of levels off, midpoint in RK4, you get roughly the expected slopes. After that, it sort of levels off. Where this levels off depends on the noise properties of the data and a range of other things. The plot on the right shows swapping between integrators. Let me just not get into that, but you see sort of similar trends. So the point here is that Euler chokes. It's a good discrete model, but not a good continuous one. And you can easily see this by checking the convergence test that we put forward. Midpoint and RK4 are better. I'll say a little bit more. The main contribution here is the methodology to evaluate convergence tests, because we have examples where Euler's fine, where midpoint can choke. So there's some other. It's not just that Euler's bad, midpoint's good. But we can test and we can see. Sometimes Euler's fine, sometimes midpoint's not. So the results show that the usual methodology in machine learning, which is evaluating training and testing curves, does not yield, in general, models that are meaningfully continuous. And so if you're trying to do scientific machine learning, that's a problem. Maybe if you're doing regular machine learning, that's a problem too, and I'll have an illustration of that. Having a peak illustrates that essentially the model's overfitting discretization of that time step. And so I think there's a lot of work here to be done to evaluate sort of model qualities that you want to be continuous in space and time, or space or time. And you know, if you can use that to develop models, or you can use this approach we have as a diagnostic to assess if the model's overfit to that temporal time step. Here's a picture to illustrate the continuous in depth. There's some basis functions, and we have some extensions. So I think this is a tip of a nice iceberg. Let's say that we don't care about scientific machine. I really just want to classify cats and dogs, and I want to do it on a cell phone. And you have a different cell phone than me, so you have more memory than me. And I'm a cloud provider, and I just want to train a huge model, but I don't want to train a model for every version of a cell phone that comes out. And the point is, for every version of a different memory structure, right? I might want models that behave gracefully as a function of memory size of the constrained model. So can we use this idea? And the answer is going to be yes. So the plot here I have is roughly the same plot I had before, except the plot before has log scale and delta t. It's the way scientific computing people, I think, would present this sort of problem. This is the way ML people would present it. There's a depth parameter. So this is not time, but it's really 1 over delta t. So it's a depth parameter, numbers a layer in your model. There's a test error. They have a training and test set. This is a test error, but this is the analog of that plot. And so you can now apply this on CFAR10, which is an image data set that's of interest in machine learning. And what you see is that if you use the Euler method we use that fails that continuity test. So here, this is images. There's no continuous model under the hood, but we're hypothesizing it. We're saying I want to work within a class of continuous models. You know, Euler does better, boom, it does very well at depth 32, and then it gets worse, and it gets better, and it gets worse, and it gets better. I mean, it's all over the place. Whereas if you use the RK4 version, it gets better, and then flattens out. And so, you know, if I want to give you a model and I want to behave gracefully as a function of depth, and I want to be good, oops, and then good, and then maybe if I get down to depth 16 or 12 or something, get gradually worse, but not totally choke. I could do that by working with a continuous model, so using this methodology. So I think this is an example that if scientific ML people don't engage ML people more generally, ML people just do their own thing. But even just for an ML metric, the idea that we got from looking at ContinuousNet's useful, just, you know, even for classifying cats and dogs. So we've applied this in a bunch of other scientific ML settings. And as I said, it's not just that Euler good, Euler bad, RK4 good. We have a sense of how this behaves for different differential operators and more complex problems. And so a lot of this is sort of work in progress that we're looking at. And let me just sort of, in the interest of time, skip over that, but just mention that we have some other examples of how that will perform on other types of sort of continuous models that are more complicated than that relatively simple one we put up. So in the last just couple minutes, I just wanted to mention some other related developments. So what we have is 2 examples of where I think a straightforward coupling of scientific methods and machine learning methods has failure points, and then, you know, how to address those failure points in ways that are non-trivial qua ML methodology, but also will yield to better results in terms of the scientific methodology. So here, let me talk about spatial and temporal modeling, sequential modeling. And time really doesn't appear much in machine learning theory. To first order and to second order, there's been some work. And just to put up a few things, so RNNs are a class of models that deal with sequential data in a certain way. Could be time, could be DNA sequences, but where there's something that's plausibly a quote time series. You can view RNNs as a dynamical system whose temporal evolutions are governed by a certain set of differential equations. There's a hidden state H, there's a sigma, which is some nonlinearity. There's a matrix that, you know, couples hidden to hidden. There's a hidden to non-hidden, an offset. A lot of machine learning people spend a lot of time talking about this sigma, this V. If you're familiar with scientific problems, this is like saying, is Leonard Jones, I told you I did water way back when, is Leonard Jones the 12.6 potential that in the early days, you know, you could compute a distance squared. If you cubed, and computing the square root was very hard. If you cube that distance squared, you get the 6th term. And if you square that, you get the 12th term. Why don't you use a 10.6, a 9.6, a 9.5.5? And you do it because you're modeling. That's for computational reasons. This is like saying a lot of what ML people do is to spend time. Should I worry about the details of it? Is it 12.6 or 9.6? So that's sort of like what this B and the sigma are doing. If you're not familiar with that, it's sort of weed level details of the model that sometimes are made for computational reasons and sometimes make a big difference scientifically. So we have a version of a continuous time recurrent unit that describes the hidden state evolution. There's a well understood linear component plus a Lipschitz nonlinearity. Lipschitz is a way to quantify niceness. And the goal here was to do as well as state of the art on training and test curves, which is what ML people care about, but really get a more robust model. And so the long story short is these numbers will justify the former claim. It's good compared to state of the art. But I think the more interesting thing in general, but also for scientific ML is because the form of this, you're really robust with respect to a range of input perturbations, some random and some sort of adversarial. And I think that is very different than a lot of the way ML theory and practice are set up, but it's an increasingly important thing just on the ML side, but it's critical on the scientific ML side. We followed that up with sort of a noisy RNN, which said, can we use ideas from stochastic differential equations and fold a little bit of noise into the training process? So a lot of people add noise to the data and so on. We did it in a very particular way, where we could view noise injection as a stochastic learning strategy to improve the robustness. And so I'm not going to sort of go into the details, but it's a similar setup in terms of the form of the model. And we're able to do that and apply it to a range of things. This is some numbers and a picture to justify that how it performs well on the electrocardiogram application. Theorem, the noise injection is sort of implicitly giving you a statistical regularization. We have other results where that theorem is made in a stronger context. This is actually a more complicated model, and so we do it in sort of a leading order Taylor series expansion context. So the noise injection, the way we did it, you're exactly optimizing a regularized version of the functional of interest. And so that manifests itself that you actually get nicer results, a more robust model, not necessarily on the training or testing data. That's the error numbers in this table. But if you were to view this in sort of model space and perturb it, so it's more robust in model space. Something else, sort of long expressive memory, go from sort of 2 timescales to multiple timescales. And so a simple version of an ODE is a 2-scale ODE is given in 21. If you're familiar with this, good. If not, it's an ODE with sort of 2 characteristic timescales, fast variables and slow variables. Solving stiff ODEs is hard, as you know, probably. You can generalize this to a multi-scale version, and we have that, and you can learn sort of long time scale sequences. So these are just things we have in the pipeline. Let me wrap up. I think the grand challenge here is we want to combine data-driven models and scientific models in a way that's interesting or principled for machine learners and for scientists. And if you're interested in this, I think this is a nice sort of initial example of how to do that. And I think it's the tip of a big iceberg. There's a lot more work to be done. And if you're not I mean, I work at, LBL also on this projects there. And as I said, sometimes the way I try and frame it is, what can you do for me? And even if I'm interested in what you're doing, I think asking that question is useful because scientists sometimes say they want to just solve scientific problems and machine learning is just a tool. And if you treat it like a tool, machine learners will walk away and do NLP or CV or something. If you try and engage them, there are non-trivial problems that if you solve in your scientific context will be useful for them and they will find interesting, whether it's the example of the CFAR or there's other examples. And so if you want to get ML methodology and strong domain-driven models sort of cooked into ML methodology in a more integrated way, I'd encourage you to use this as an example and extend it, but try and meet machine learners halfway and don't just say, how can you solve my problem, but how can we get sort of, that's not how numerical analysis and scientific computing evolved, right? You really had to get into the weeds of the computer and the architecture, and when you had a good two-way discussion there, you had real advances on the science as well as sort of on the non-scientific aspects, the mathematical aspects. So I think we're in a similar situation here. And so hopefully this is how things will evolve. So thanks a lot for your attention. And if there's any questions, I'll be glad to stay around and answer them for a bit.
Thank you. Thank you so much, Michael, for the great talk. It was very interesting. Okay, let's have a Q&A session. There's no question in the chat room, so unmute yourself if you have questions. So my brief question on page 18, if you go back, you nicely draw the graph of the loss functions with epsilon 1 and epsilon 2. And I was wondering, what are those epsilon 1 and epsilon 2?
There's a couple different things. These could be random axes or the lead two eigenvalues of a Hessian, for instance. You get stronger results if you look at the lead two eigenvalues of a Hessian. We're looking at a million-dimensional loss landscape in 2, or if we try 3 dimensions. So there's no perfect way to do this. So I don't want the picture to be a proof. So there's a bunch of evidence. This is sort of a proof by picture. But this is choose, either random or in this case, axes that are stochastic estimates of the lead axis of the Hessian.
Got it. Okay. So you chose like the first one or two, the eigenvalues, and
yeah, and so as we have code at a Hessian and pi Hessian to do a range of Hessian-based methods, and so if you're interested in these sort of Hessian-based methods, we can do training in 2 times backprop time with randomized linear algebra variants of Hessians. So these are stochastic estimates of the top eigenvalues, eigendirections of the Hessian.
I see. Got it. Oh, that's very nice way. Okay, we have a question from Emmanuel. He asked, thank you for the nice talk. A curiosity, do you think it is possible to, instead of using a new term in the loss function, include physics as an equation to be respected between layers of a neural network?
Yes. People like to include it in a loss because then you're optimizing a loss. But one of the big changes in ML in the last 10 years, whatever, is it used to be the case that people would say, do a lot of feature engineering and then call a method, decision trees or ensemble or kernels or whatever. And people shifted to saying, well, design architectures and give yourself lots of parameters and let the features sort of pop out. So you're shifting it from feature engineering to architecture engineering. So my interpretation of the question, I guess, is can you include layers that are more domain driven or physics driven? I mean, in some ways, that's what convolutions are doing. They're saying if you have an image, there's some local geometry, so smudge over that. And in some ways, that's what RNNs and subsequent developments to RNNs and then attention modules and transformers are doing in NLP. They're trying to capture the sequential ordering of language. And so, question, can you do that in sort of a more fine-grained way, knowing that I have a differential operator that's a parabolic or hyperbolic operator and cook that into the individual layers or something? I think the answer is yes. I mean, a different thing you could say is I know that I have strong symmetry properties, and so cook that into the layers. So I think that's the answer. That's yes also. I mean, so Prabhat and some people at LBL had some nice results where they were doing something that sounds like that for state-of-the-art climate modeling. And, they needed to use these attention and convolutional models, but not off the shelf. They needed to really tailor it to the science and got some non-trivial successes there. So I think that's a nice direction. I mean, I think how those architectural changes couple with the optimizers is still a good question, because if you make those changes, you might flatten gradients and introduce other problems. But the short answer is yeah, I think so.
Great. Emmanuel, he did thumbs up, so that's great. Is there any other questions? So you can unmute yourself and ask questions. I really like the talk, the talk you gave in a way that, I mean, you're introducing some way of looking at, some perspective of looking at the ML and physical science together. Bringing the classical numerical convergence study or some continuation method, applying the continuation method in a way of solving the optimization of the training of the neural net. So I really like that.
Yeah, and I think that's a good direction and one that's sort of well suited. I mean, it's in general, but in particular, if you think about these things from the problem of scientific machine learning.
Right.
I had one question. As you talk about, or you talked on some differences between the methods and the kinds of models and the approach from a machine learning side versus a scientific side, Of course, there's some real differences in the types of models that both kind of approaches develop. One's more focused on creating a model that can be run by a computer, and the other is more of a, what can I publish and study and understand the theory behind? Do you have suggestions or thoughts on the role of machine learning as maybe fitting somewhere else in our process to help us identify or come up and think about new theories, or where there's correlations and concepts that we may not be intuiting without the machine learning approach?
So I'm not sure exactly what you're asking, but let me give an answer to something that might be that, or by analogy or something. I mean, I think it sounds like you're saying, you know, you're sitting on the science side and you're saying, how should I look at this and how can I do something interesting or useful with this, right? And I think that's a fair question. And I mean, an analogy, I mean, is who cares about scientific computing and optimization and numerical analysis, right? You know, but having a fixed infrastructure of support for those sort of things, and people who self-identify as doing numerical analysis or scientific computing, and having them talk to you and say, I want to publish in my own area because I like, this is what I like, but you know, I'm going to be informed by your problems. You never really get a feedback loop, right? And so then they ask questions that would be different than if they didn't talk to you. So it's hard to say exactly, and then you get, I mean, computers are do a lot more these days than invert 10 by 10 matrices, which was the big use case in 1940 or 50 or whenever, right? So it's hard to know what developments will happen, but I think having that sort of in the process, you know, is sort of a critical for a feedback loop. I mean, I think there's just a lot of scientific questions that people would ask of the methods that people tend not to ask in machine learning venues where you don't have that feedback loop. And I think that, you know, that's a hard thing to support, especially maybe for, I mean, I'm assuming that, you know, you guys are a little bit like LBL, right? It's a big lab and there's a history and stuff. But I think, you know, having that be at DOE sort of a high enough priority that you say, I'm going to invest in a head count and these people are just going to do ML. I'm not going to, but they're going to go to lunch with me and inform what I do and figure stuff out. And it's hard for me to imagine that you won't have analogous sort of successes like you saw historically with scientific computing. And, you know, where those would be, I tried to sort of give you some examples of where I think they might be. The details of the optimization, I mean, how you deal with hard versus soft constraints, continuous, and I think, I mean, it's useful more generally, right? Because if you understand what it means to be meaningfully continuous in time, that actually would be much more useful for just ML people. If you're doing self-driving cars and you want to understand, you know, flow fields of LiDAR detectors and so on. But some of those LiDAR detectors are going to feed back to some other scientific use cases. So I think, so that seems, I don't know if that's what you're getting at, but it seems like, you know, having that be part of the feedback loop and not demand that sort of every time someone has something, it's very strongly tied, but having a little bit of a longer leash there seems sort of crucial, because there's a lot of green pastures for ML people to go off and do, right? So, I mean, and some fraction would like to do the scientific problems, but giving them a sort of a long enough leash that they can do that and then feedback seems to me to be sort of an important thing there. So I'd say it's more of a structural thing than do this particular direction, because the ones I laid out may be right or wrong, but that seems to be the bigger issue, if that's what you're trying to get at.
All right, sounds good. Another question from Brian. Great talk. Was wondering from your perspective, what the main value PINNs, PINNs bring over traditional numerical methods, since they only approximately solve the equations, since obviously traditional numerical methods can also solve the same PDEs.
I mean, I don't know, what value does the computer have? I mean, people thought it was going to be to invert 10 by 10 matrices, and it just opened up lots of other questions. I mean, I don't want to get in the middle of a PINN debate. Some people love them and some people hate them. I mean, I think they're a nice initial result to sort of bridge this gap. And I don't think they're the final word, and they'll improve things. But I don't think the question's to solve a PDE. I mean, here's a question. If you have access to a factor of 1 million more data than you had 20 years ago, and you wanted to solve PDEs in some way, what would you do? I mean, if PINNs is a framework that begins to allow you to couple to ML methodology, and that's what ML does, right? And so it's not to do a better job on something someone was doing 20 years ago. It's to do a better job on something different. And that something different is usually where the data is cheap and you can apply ML methods. And if there's an impedance mismatch between the ML methods and the traditional PD methods, you're not going to deliver on the promise. But if you decrease that impedance mismatch, you can. So I wouldn't view it through the lens of, oh, I have an old school PDE that I wanted to solve 30 years ago, and PINNs will do better at that. You know, what different class of problems that are PDE related can they solve?
Yeah, if I can add something to that, the PINNs, yeah, if you're just talking about the force solution process of the PDE, then maybe not as accurate as the traditional method, but it does give us a innovative way of looking at the inverse problem, which we couldn't do with the traditional numerical method. So there's some benefits, definitely benefits through the PINNs there. Okay, is there any other questions? All right, if not, let's thank our speaker today. It was a wonderful talk. I really liked it. Thank you so much, Michael.
No, thanks for having me.
I'm glad that you accepted our invitation to the talk. Okay, thank you. Great applause.
All right, thanks a lot.
To you. And okay, let me stop the record button.